Hi, so I'm going to walk you through the lab write-up, so make sure you understand what is happening for the lab so you can do a correct analysis. There's a lot of little detail here. It's easy to get confused, but if you read through this carefully and follow along with this video, hopefully things will be clarified. So I'll let you read the background, but there's two major problems here. You want to find the acceleration of a car as it rolls down an incline using a stopwatch and a meter stick. Okay, well, we didn't use a meter stick, but you had the scale on the track. So you have that information. I want you to solve it. So a part of the write-up right here is your procedure. You can explain what's happening in the video. You don't say watch the video, you just say, let a car roll down from the top of an incline, measure the time using a stopwatch, etc., etc. Don't put any data, don't say how far it is. But what I want you to really work out in advance, and right here, what equations are you going to use to solve these problems? So this is part of your kinematics practice. You got acceleration, you're looking for acceleration here, you know a time, you know a distance, you know a third piece of information, and then I want you to show what equation would be most appropriate. Work it out through the process. Don't just assume that the acceleration equation is something if it doesn't fit your information. The second problem is I want you to find a new position. I'll call it x prime, okay, that's different than this position. So x prime, you're going to figure out based on knowing the acceleration, knowing what your final speed is going to be. We want the final speed to be 150, and knowing something else, the third piece of information. I'll let you determine what that third piece of information is, but just to make sure you're clear, if this is the ramp, right, and this is 0 down here, you want to figure out where on the ramp do I want to put this so when it goes down at the bottom it's going 150 centimeters per second. So there's where one piece of information. You already know the acceleration of the ramp because you found it from part A. You need a third piece of information. That should be fairly clear. Let me tell you, it's not the time that you use for the first part because the other time was you were up on the ramp further. So that time doesn't correspond to the second problem. And again, in the procedure, write down what your equation is used to solve that. So let's go where you're going to put the data. So you will watch the video and you will get the information on distance, put up appropriate uncertainty. You will get times. You'll have to do that yourself, put an appropriate uncertainty, average, and then random error and show a calculation there. Pretty straightforward. Acceleration, you're going to show the equation you chose, put in the appropriate values, come out and round properly. So let's talk about uncertainty. So there's uncertainty coming in your measurements, especially your time measurements and even your distance measurements. So we want to understand that whatever value you get here, there's going to be a plus or minus delta A. So this part, you're going to use propagation of error, where you're going to solve for delta A over A, knowing the equation that it's really 2x. If I solve for the equation from here, this is kind of giving you a hint what equation to use. A is equal to 2x over t squared. So use the rules for propagation of error. Review them back in your notes if you need to. But I'm going to leave that for you to do. If you do things correctly, okay, so this will give you a percent. So your percent uncertainty might come out to be, as a decimal, maybe between 0.05 and 0.2. Again, depending on how much spread there is in your times. Don't include a time if there's a clear outlier. You just mispress the button or something like that. So if you have a moderate uncertainty in time, the fact that we square it doubles that uncertainty. We should not be above 20%. As such, when you go to do your absolute uncertainty in it, you're going to take whatever your percent is, let's pretend it's 20%, and you're going to take it and multiply it by the A that you found over here. So that value should be no more than, 20 or so absolute value. It's probably less than that. Once you get this value, round it to 1 sig fig. And then if that sig fig turns out to be, let's say, 1, then you round this to the nearest 1. So round your acceleration appropriately, plus or minus this value here, and make sure the precision matches up. All right, that's all for part A. Then for part B, once you have that acceleration, you're going to solve for where you're going to put the object. So you're going to solve for an x. Again, put equation, put in appropriate numbers, and then solve for it. So then the last part of the video is verification. You have some position. So we started on the video at 200, so your position has to be less than 200. Let's say you say it's at 100 centimeters. So what you'll see me on the video do is I will release the car from various distances that approximates what you might predict. So if you predicted 100 and I'm testing it from 105, then my speed is going to be slightly greater than you predicted, so you can make a slight adjustment. We're not looking for perfection here. So when you see it on the photo gate from the video, put the actual speed, calculate the percent difference. And then lastly, you have some conclusion questions. This is looking at your percent uncertainty and velocity. So read this information very carefully. You can follow this, I believe you can. And once you do that, you can get what the expected uncertainty and the velocity is based on your position, which comes from the uncertainty and acceleration that you found earlier. And then the last question asks, so if you're looking for 150 and the photo gate says 147, well, you might say they're not the same value, but your 150 has a plus or minus value to it that you got from up here. So if there's significant overlap as described here, then you can argue that they're essentially the same value. So it's a good practice for you to do. And then discuss a major source of error. Be specific on that and how you think it affected your results. Did it make it too high, too low, something like that. Okay, good luck. Collaborate with someone from your class if you're not sure, or message me as well. Morning, everybody. I'm going to show you some data for the accelerated motion lab of a car going down an incline. So this is a variation on a lab or activity I did last week. In this case, we're going to make measurements of how far a car travels and how much time it takes, and then from that you're going to figure out two things. You're going to determine the acceleration of the car along the ramp, and then once you have that acceleration, you're going to figure out where to place the car on the ramp such that when it gets to the bottom it's going a prescribed speed. That speed will be on your lab, and then you're going to use that speed as part of your information to help you figure out that position as measured up from the bottom of the ramp. So let's turn to then the actual measurements. So I'm going to let the car roll down a ramp 5 or 6 times. You're going to time it. I will show you what the distance is traveled, and then the rest is just calculations and analysis. An important part of this lab will be propagation of error. There will be uncertainties in your distances and times, especially your times. So you have to show how that propagates through when you're calculating your uncertainty and acceleration, and ultimately even the uncertainty and velocity. Lastly, you're going to make a prediction of position so that's going a certain speed. Normally we would test that in class to see how accurate results are. I'm going to basically test it with the photo gate by releasing the car from various positions, and you match whatever position that I do to your prediction, and then see how close the velocities really are. I'm going to choose positions based on what I expect the actual one to be plus a range above and below. We'll see how that works. So this is our setup. So I have the car sitting on the ramp, tape's just there to hold it, and it's going to roll the way down and hit that aluminum block at the bottom, which is at position 0. I will note where this is starting for each of the 6 or so trials, and then I will say 3, 2, 1, and then release or go, and that's when you know to start your timer. I will then follow the car down, and you know when to stop it, and repeat that 6 times. Okay, so let's start with the initial position. So I'm going to go based on the plunger right there, the tip of it, because that's what's going to hit the block below. It's at position 200. Now I don't know it's exactly there, so add an appropriate instrument uncertainty to the 200 centimeters. Okay, so let's get ready to release. 3, 2, 1, go. Okay, that was trial 1. Let's do trial 2. 3, 2, 1, go. It's nice the way that bounces back up. All right, third trial. 3, 2, 1, go. All right, hopefully you can hear that clearly. Fourth trial. 3, 2, 1, go.
Okay, number 5. 3, 2, 1, go. Nice. I love this car. And the last one. It's trial 6. 3, 2, 1, go. Okay, so the next segment of the video will be based on your predictions of where to place the car. So let's be clear. The car starts here at 0. You're going to figure out how far we place it up the ramp such that when I release it, it's going to be going a certain speed, an instantaneous speed. This requires knowledge of not only how far it travels. You're going to predict that. You're not going to have any time. You don't know how much time it's going to travel. The times you just took are based on the 200 centimeters of distance of travel. So you're going to use your acceleration that you found in part 1 plus 2 other pieces of information that you know about the motion to help you figure out how far up the ramp it'll go. All right, good luck with that, and then we'll do the next segment in a few. All right, let's do our tests of our predictions. I'm going to release the car from 5 or 6 different positions at 10 centimeter intervals. You're going to match the position that comes closest to what you predicted. Now, if I'm going to start at 110 centimeters. If you predicted yours was like 98, you're going to have to make an adjustment. That 98 is going to be too low. If you predicted 115, you're going to take the halfway value between my tests for 110 and 120, and so on. So we're going to get the speed directly by looking at this photo gate. Okay, so I have a photo gate right on here, a little fin that passes through this photo gate and gives us an instantaneous speed just before it hits. So let's start. I'm going to start at position 100. We're going to do 1 trial per. So there we are at 100. Release, passes through, and our speed is 129.8. Okay, so let's do our next one. We're going to go to 110. Oops. And the speed was 135.1. Okay, now let's go to 120. And again, choose the position that comes closest to your prediction. And that's, oh, that didn't quite work out. I don't know why I recorded 52, so let's do that again. We'll attribute that to a glitch. Let's try 120 again. Okay, so it's going 140.8, so we're getting closer. Reset. Hard to do this with just 2 hands. All right, we're at 130. And 147.0. Okay, let's go to 140. Okay, 153.8. So we're past our speed. Okay, let's go to 150. $158.7. We go to 160. $163.9. And I'll do one more. I just lost my pen. We'll do 170. Bear with me. I don't want to turn this off because it just makes uploading it more of a pain. Alright, so let's make sure I reset it. I did not. And let's release it from 170. All right, and we got 166.6. So hopefully your predictions fell between 100 and 170. Now let you calculate, or you have the speed, I'll let you calculate percent differences and then discuss why you may, or how far you were off and why that might have been. All right, so if you have any questions, make sure you ask.